Good evening everyone. So today I will be teaching you about the temperature dependence on the rate of reaction and also about the Arrhenius theory. So basically, to start with, I would like to tell you that many of us have seen that milk gets spoiled faster in summer season, whereas it stays fresh for longer period of time in winter season. Same is the case while we cook food. If we cook food on high temperature at high flames, it will get cooked easily in less amount of time. But if we cook food on low flame at low temperature, it will take more amount of time to get cooked. So what is something which is changing here? That is temperature. So we can say temperature has got something to do with food and how it changes the time. So basically, this is not only true for the food we eat but also for the chemical reaction happening. So all the chemical reactions which are happening are temperature dependent, and I am going to explain you what is the role of temperature on the rate constant of the reaction and how Arrhenius theory explains this. So to start with, many scientists have come up with different hypotheses of temperature and rate constant dependence. One of them was J.H. Wendt, who first of all told us about the temperature dependence on the rate of reaction. But somehow we could not interpret it or give physical significance to that. So a Swedish scientist, Arrhenius, came up with a new equation, empirical equation, and then he stated the Arrhenius equation, and basically he was the first one to give us the Arrhenius equation in its empirical form, and also to tell us that this is how a reaction happens, and physical significance of that reaction is given by Arrhenius. So if we start with, so we all know Arrhenius equation is K is proportional to E raised to minus EA by RT. Okay. So here the first term, that is K. K is the rate constant of the reaction. Now, if we further simplify this equation, we remove the proportionality constant. This equation will be written as K is equal to K naught E raised to minus EA by RT. Now, some people write K naught, some people write A. So, what is this K naught or A? That is the Arrhenius constant, or we can say the pre-exponential factor. Then we are having EA. What is this EA? EA is the activation energy, and the first question which will be coming to your mind is, what is activation energy? So I will be soon telling you what is activation energy. R is the universal gas constant, and T is the temperature of the reaction. To begin with, what happens when you heat a particular substance? When we heat it, what happens is we are providing temperature. Basically, we are supplying energy. So as and when the molecules receive energy, the kinetic energy is increasing, so the molecules will move more frequently. As the molecules are moving, their collision will increase. So depending on that, we have studied in collision theory that in order to transform reactants to product, we need a fruitful collision between two molecules. So when we are supplying energy, when we are increasing the temperature, basically what we are increasing? We are increasing the collision, or we can say the fruitful collision between two molecules. As this collision increases, the probability of converting a reactant to product increases. But there is also one thing, that molecules need certain amount of energy in order to cross the energy barrier and convert to products. So this is what is activation energy, the energy which is supplied. In order to tell it to you in very simple terms, let's say you are studying in a class and you are having an exam. Okay. In exam, the maximum marks you can score that is 100. Okay. Now, in order to pass the exam or in order to be eligible, you will have to score say 1/3 marks, that is 30 marks. But let's say you didn't prepare well and you scored less marks. So somewhere you are getting around 27 marks. In this case, what will happen? What will your guide or your professor do? Basically, for 3 marks, nobody is going to fail you, right? So you will get grace marks. How many grace marks you will get? 3 marks. If they give you 3 grace marks, what will happen? You will pass the exam. So the activation energy is similar to the grace marks which you are getting. So reactants are at a particular energy at ground state, and when we supply energy from outside, they reach the threshold limit and they convert into products. And to more precisely draw the graph of activation energy, we can draw it in this way. Let's say this is the reaction coordinate. Okay, and this is the enthalpy of the reactants. At a particular instant, let's say we are having a reactant R. Okay, so this is the reactant R. R is at its reactant enthalpy in its ground state. From here, we supply certain amount of activation energy and R reaches a particular transition state. After that, it converts into products. Let's say P. Okay. So, basically what is happening? Here, R has reached the transition state. Here, whatever it is there, that is the reactant's enthalpy. And whatever we are supplying from here to here, that is basically the activation energy. Or we can say EA. Now, what is the total energy required in this reaction? Is that the activation energy or the reactant enthalpy? The total energy is the addition of both reactant's enthalpy plus the activation energy, and that total energy is called the threshold energy. Now, if I tell you to, so this was just a basic definition or explanation of activation energy. To tell it in more scientific terms, we can say that the additional energy required to break the old bonds, or we can say the additional energy required by the reactants to reach the transition state. That is called the activation energy of the reactants. Now always remember, the graph of enthalpy versus the reaction coordinate for activation energy will be a bell-shaped curve always. Okay, any other curve which is there is not eligible for the reaction. If I give you one question, like let's say, in which of the following activation energy will be 0? So I will give you many graphs. First one is like this, second is like this, let's say third one is like this, and fourth one is let's say like this. Okay, and these are your options A, B, C and D. What will you do? So as I told you that this graph, it should be a bell-shaped curve. So which of these is a bell-shaped curve? That is B and C. So completely A and D are not eligible. So cancel out. Okay. Now here we can see these two are bell-shaped curves. But here reactants are at their ground state, and from there we are giving them some energy to reach the transition state. So here we are having some amount of activation energy and it is not 0. But here we can see reactants are already at transition state. So from from here they will directly get converted into products. So do we require any more energy? No. So here in this case activation energy is 0. So this is the correct answer. Okay. Now this was we were talking about the Arrhenius equation. Let me write it to you in a traditional way by taking logarithm on both sides. So when we take natural logarithm on both sides, we can write ln k is equals to ln k naught minus Ea by RT. Okay. The graph of this equation, it should be similar to y is equals to mx plus c. So this graph will be a straight line plot. Here on x-axis we will have 1 upon t, and on y-axis we will have ln k. Okay, and this graph would look something like this. Now the slope of this graph will give you the value of minus Ea by r. Okay. Now for a particular reaction happening at a temperature T1, we can write ln K1 is equal to ln K naught minus Ea by R T1. Similarly, if the reaction temperature changes, the rate constant will also change. For the same reaction, we will write ln K2 is equals to ln K naught minus Ea by R T2. Now, if we minus these two equations, subtracting these 1 from 2, we will get ln K2 by K1, that is equal to Ea by R 1 upon T1 minus 1 upon T2. And this is the form of equation we write when we want to know the two different rate constant at two different temperature for one particular reaction. Okay. Initial form of this equation was K is equals to K naught e raised to minus Ea by RT. If we plot this, then the plot would look something like this. Okay. Here it is K versus it is temperature. This is how it looks. So, as and when we will learn more, we will get to know that these are temperature sensitive reactions. So, if for this type of curve, for straight line curve ln K versus 1 upon T, there can be like this curve and there can be like this curve. So, we can determine if the slope is steeper. Here the slope is a bit not steep, and here the slope is a bit steeper. If the slope is steeper, means high amount of activation energy is required, means the reaction is highly temperature dependent. If the slope is like this, hence that it means it is a less temperature dependent, but still on changing the temperature, on changing the activation energy, the temperature will change. Thank you.